Okay, so this is going to be a Green's theorem problem. So this is the problem. So let C be the circle, x squared plus y squared equals 16 with counterclockwise orientation. Compute this line integral here. Okay, so it's a line integral over a closed curve. Okay, so anytime you see a line integral over a closed curve, you want to first make sure that this is not going to be this is not a conservative vector field, and I'll let you check that this is not a conservative vector field. The x derivative or the y derivative of this is 6y squared. The x derivative of this part is minus 6x squared, so those aren't equal, so it's not conservative. If it's conservative, then it's equal to 0, remember. Okay, so we're going to use Green's theorem, and Green's theorem says that this integral is equal to the following. This integral is equal to the integral over d, where d is going to be a region enclosed by this circle. So it's going to be the disk of radius 4 centered at the origin. And now it's going to be the partial derivative with respect to, the partial derivative with respect to x of this term. So the partial derivative with respect to x of this term is minus 6x squared minus the partial derivative of this term with respect to y, which is minus 6y squared. And then we do dA. So remember, this is what Green's theorem says. It says that the integral, if you do this line integral, p dx plus q dy, then this is equal to the area integral over the region D, which is the region contained in C, qy, that's qx, qx minus py dA. So up here, the p is 2y cubed and the q is minus 2x cubed. Okay, so this is what Green's theorem says. And remember, you have to make sure that the orientations match up. So to use Green's theorem, this curve needs to be oriented in the counterclockwise orientation, which is what we have here. Otherwise, you need to multiply the area integral by minus 1. Okay. All right, so then now we just have to compute this. Well, this is clearly a polar coordinates integral because we're integrating over the disk of radius 4 centered at the origin. So this is going to be minus 6 times the integral r equals 0 to 4. Square root of 16 is 4. Theta equals 0 to 2 pi. So now the x squared plus y squared, that's r squared. And then you have r dr d theta. And I'll let you do this. This is equal to minus 768 pi. Okay, so again, let me just say what Green's theorem is once again. Green's theorem says that if you are doing an integral over a closed surface with counterclockwise orientation, that's what this up arrow here means, and it's p dx plus q dy, this is equal to the area integral over the region D. D is the region that is enclosed by C. This is qx minus py. This is the derivative of q with respect to x. This is the derivative of p with respect to I dA. And once you get this integral, you can change it to polar coordinates if you want. Okay, but remember, for this formula to be true, this curve has to be in the counterclockwise orientation. Now, if the curve is in the clockwise orientation, so that you might write the integral like this, the curve is in the clockwise orientation. Okay, so the down arrow here, this arrow means it's in the clockwise orientation, then you have to put a minus sign there. Okay, so you can still use Green's theorem even if the curve has negative orientation or clockwise orientation. You just have to make sure you put the minus sign. But the standard way to write Green's theorem is like this, where the curve has a counterclockwise or positive orientation. Again, the closed line here means it's an integral over a closed curve, and this arrow means it has counterclockwise or positive orientation. Okay, and Green's theorem is a theorem that only works when you're dealing in the plane. So this only works when the curve lies in the xy plane. Okay, if the curve goes into three dimensionals, if C is not a plane curve, then this formula does not work. You have to use Stokes' theorem. But when the curve is in the plane, you can use Green's theorem, and this is the theorem to use.